Hello everyone, welcome back. In this example, we're looking at another 2x2 system of linear equations that we want to work together to solve. So the first equation in our system here is 5x minus 2y is equal to 4, and our second equation in our system is negative 10x plus 4y is equal to 2. And so we're going to solve this system or attempt to solve it algebraically using either our substitution or our elimination techniques. And we have to decide which technique we want to use. If we wanted to use the substitution technique, we'd have to solve either of our equations for x or y, but it looks like in attempting to do so, we'd encounter some fractions. So let's try to use our elimination technique instead because we want to try to avoid fractions as much as possible, right? So if we're using our elimination method, we have to decide first which variable we want to eliminate. Let's just go ahead and try to eliminate x here. It doesn't look like it makes too big of a difference either way. And so if we want to eliminate x from our system of equations, we have to take some combination of our first and second equation, add that combination, or you could subtract it, add or subtract that combination together in such a way that the variable of x actually disappears. And so the way we always kind of set this up is we want to multiply one or both of our equations by whatever numbers are necessary so that the number in front of x, or the variable that we want to eliminate, is going to be the same but opposite in sign. So we need to think about either turning this negative 10x into a 5, or this 5 into a 10, or some number that is a common multiple of 5 and 10. And so in this case, it's going to be easiest, I think, just to multiply our first equation by 2, and then add it to our second equation. That'll make the coefficients, or the numbers in front of x, the same, but opposite in sign, so that when we add our equations together, they cancel each other out. So once again, the steps I am taking to set up our elimination method is we're going to take 2 times our first equation and add to that our second equation. So 2 times our first equation gives us 10x minus 4y is equal to 8. And our second equation, we're not manipulating at all, is still negative 10x plus 4y is equal to 2. And so we did all this setup to make sure that we eliminate the variable of x from our system. Now let's go ahead and add these equations together and see that that happens. The positive 10x does get canceled out with the negative 10x, but we have even more cancellation than that occurring. The negative 4y also gets canceled out by the positive 4y. So on the left-hand side, everything has been canceled out, leaving us 0 or nothing. But on the right-hand side, we're still adding 8 and 2 together, and that gives us 10. And so now we've encountered this algebraic statement that says 0 is equal to 10, but we know that that is not true. That is a false statement. And so now we have to know how to interpret this situation. And so if we go back to the pictures of the 3 scenarios that we may run into when solving a 2x2 system of linear equations, we can identify which of these pictures we are in. So remember, the first picture is where we have a single solution where we can actually solve for x and y, and that corresponds to our lines intersecting. That is clearly not the situation we are in. The second picture corresponds to when we have no solutions, and that's when our lines are parallel. That is the situation that we are actually currently in. We sort of can see it when we multiplied the first equation by 2, but if we took a moment to rewrite each of these equations in that slope-intercept form, what we would find is both of these equations have the exact same slope, but they have different y-intercepts. So we really do have parallel lines in this system of equations, and that's why we encounter this false statement algebraically. These parallel lines will never intersect, so we have no solution. So we don't write false, that's just how we kind of interpret that 0 equals 10 part. What we want to say as our final answer in a situation like this is that we have no solutions, or no solution. Hey everyone, we have another example of a 2x2 linear system of equations that we want to work together to solve. And so our first equation in this system is y is equal to 2x minus 1. It's already in that nice slope-intercept form. And our second equation in this system is 6x minus 3y is equal to 3. So when we are solving our systems algebraically, we can either use our substitution method or our elimination method. We just have to identify which method we think is going to be the most efficient, depending on that initial setup. But it doesn't really matter in the end. Either method should give you the exact same answer. So because that first equation is already solved for one of our variables, we have y written in terms of x. Let's go ahead and use our substitution method. We're basically already set up for the substitution method here. So we can now substitute into our second equation the information that our first equation tells us about this system, that y is interchangeable or can be replaced with the quantity 2x minus 1. So I've rewritten that second equation, 6x minus 3y equals 3, making the substitution that y is equal to 2x minus 1. And now we are left with this equation involving just the variable of x. So let's go ahead and try to solve that. So we're going to have to distribute that factor of -3 throughout our quantity in parentheses. And so that lets us expand the left-hand side as 6x minus 6x plus 3. Well, those 6x's cancel each other out. And we are left with the statement that 3 is equal to 3. So in our previous example, we encountered a similar statement involving no variables at all, but that one was something like 0 is equal to 12, a statement that is clearly false. Now we've encountered a statement that is clearly true. 3 is in fact equal to 3, believe it or not. And so how do we interpret that in our situation of solving a system of linear equations? Well, it's really coming down to this third scenario, the one we haven't really seen yet. And we can really show that we are in this third scenario where we have infinitely many solutions or our lines are coinciding by taking a moment to rewrite our second equation in slope-intercept form. So let's go ahead and add 3y to each side and subtract 3 from each side. So we can rewrite that second equation as 3y is equal to 6x minus 3. And now if we divide both sides of our equation by 3, it becomes y is equal to 2x minus 1, which is the same as our first equation. So our first and second equations may look a little bit different initially, but they actually are the exact same equations. So when we graph the line for each of those equations, those lines are going to coincide or land right on top of each other. And so that means for this system, we have infinitely many solutions. And so our indicator that lets us know that we have infinitely many solutions is a statement that is always true, like 3 is equal to 3 or 0 is equal to 0. So if you're solving a 2x2 system of linear equations and you encounter a statement that is always true absent of any variables, like 3 equals 3, then that's how we know we have infinitely many solutions. And the picture behind the scenes is that our lines are landing right on top of each other, giving us those infinitely many points of intersection.